All right, let's see if we can actually derive the period for a pendulum. And this deriving stuff is something we often do in physics, and you don't normally need to do it in level 3. You're given the equations and that sort of thing. So we've got a pendulum, L theta. We've already talked about the fact that the pendulum has a SHM motion for small angles, and we'll see a little bit of why with this one. So we've got the usual mg. And I think if you've looked at that one that looked at the forces on a pendulum, you'll realize that the force down is equal to mg sine theta. Now, that's the net force, and for small angles, that's approximately equal to mg theta. That might seem strange when I say that to you, but one of the things that we look at in physics is the fact that sine of theta is approximately equal to theta for small angles, right? And same for tan theta. For small angles, they're about the same. This is if you put the theta in radians. Don't forget radians. So have a look at what the radians is like for 1 degree, the sine of theta for 1 degree, the tan of theta for 1 degree, and you'll find that they're all about the same. So that's what we mean by that. So if we say that the net force acting on it, remember we just look at the horizontal component here, and again, that's why this is very much only for small angles. The pendulum is not SHM for big angles. Remember, I talked about, again, the different aspects of this little guy. But anyway, let's get back to deriving it. We know it's an approximation. So we've already said that the acceleration, acceleration is equal to force over mass. So acceleration, we can say, is equal to g theta. And we also know that that was equal to minus omega squared y, right? Y being displacement. Sometimes I use x for displacement, but we'll just use y. Well, sometimes I use d for displacement. So that just means displacement away from the equilibrium. So we're getting to a point where we can actually work out a period now with this pendulum. Another thing we can also say is that theta here we can write in terms of L and distance away. So if this is the hypotenuse, then the sine of theta would be displacement y over L. So y over L is going to be equal to the sine of theta. But we just said y over L, right? Well, no, we just said the sine of theta was equal to theta for small angles. So again, we can rewrite this equation, g times theta, which is equal to y over L is equal to minus omega squared y. So we can cancel these y's, and we're at the point where we can say g over L is equal to minus omega squared. But omega is equal to 2 pi over t. So omega squared is equal to those guys squared. Equal to 4 pi squared over t squared is equal to g over L. We won't worry about the negative. We'll drop that off now because that just was to do with direction. So let's rearrange that. We can put the t squared up here is equal to 4 pi squared. Right? Now that there, the t squared's gone up there, so I'll put the g down here and I'll put the L up here. Now if we take the square root of all that, what are we going to end up with? Well, I'm going through the paper, aren't I? Doesn't matter. It's all in the aid of trying to do this. So now we've got the t squared is equal to 4 pi squared L over g. Take the square root of both sides, and we've got 2 pi. Square root of L over g is equal to 2. And that's our formula. The thing to see here is as L gets bigger, the period gets bigger. All right, and as g gets bigger, the period gets smaller. Make sense? Yes, it does make sense. Always look at that when you're looking at a formula. going back to where we started with all this, so we've ended up with that formula. What assumptions did we make? We made the approximations that the sine of theta was equal to theta. So we were able to take our sine and get rid of it. And looking at the y over L, we were able to say that is equal to sine of theta. So we're able to get rid of we're able to again get rid of our sine of theta on that side. So there's a couple of little tricks we did to do this. You don't totally have to understand them. I just wanted to show you how we went about doing that, and that it was very important that with a pendulum the angles were small for it to approximate SHM.